Okay, so for module 5, part of which is from, if you would remember, we have skipped the a few properties of atoms and molecules, which we will be covering here. We'll start from molecular polarity. Now, just remembering a little bit from your molecular polarity. Remember the covalent bonds? We will be primarily talking about the covalent bonds, which are non-polar and polar. So polar bonds will always form between atoms with electronegative difference. For example, carbon and oxygen. Oxygen is an electronegative element, carbon not so much. So there will be an overall dipole present here. So whenever we will draw a dipole, we start from the lower electron density area and with the electron rich area. If you have a dipole in this situation, you will have a resultant dipole to electron high density from electron low density. Anybody has a question? So this is my resultant dipole. If you look at a tetrahedral molecule, CF, now we see that there are this polar bond, this polar bond, this is a polar bond, this is a polar bond, but is overall a resultant dipole present. So this is what the resultant dipole will look like. Any 3 atoms you can combine, you can add these 3 dipoles perpendicular to this plane. This dipole and this dipole, so the resultant dipole and this dipole are going to cancel out because they are going in the opposite directions. They will nullify each other. So overall, even though there is a presence of dipoles, even though there is presence of polar bonds, we see the overall polarity is 0 for this molecule. What do you think will be the polarity of the molecule if we have 3 similar atoms and 1 different atom? Do you think the overall polarity will be 0 or there will be some polarity? There will be some overall polarity. Why? Because even though these fluorines, they are going to have a resultant dipole, their resultant dipole will be a little bigger than the one with CCl. Why? Because chlorine is less electronegative, while fluorines are very, very electronegative. Actually, they are the most electronegative elements in our periodic table. So there will be an overall dipole present in this molecule. So when you're thinking about a molecule being polar or non-polar, think about the hybridization first. Based on their hybridization, you will know their geometries. If it is a tetrahedral, if it is a planar, if it is a trigonal pyramidal, if it is a bent, you will think about the geometry and then think about the overall polarity. By drawing it out correctly, drawing out the shape correctly and looking at it. So in our module 2, drawing these zigzag versions, drawing these extra bonds is a very important process that all of you must understand. Okay. Similarly, for your double bonds, we can see polarity. Both of your Cl. So if you look, if you remember on this carbon, who is the priority, the Cl or the C? The Cl is the priority because this has a higher atomic number. On this carbon between Cl and CH3, Cl will be the priority because Chlorine has the higher atomic number. And so both priorities are exactly same. Both priorities are on the same side. We will label this as a cis isomer. Cis isomer, both these chlorines are going in the same direction, in the same area. So there is a overall resultant dipole. It's not zero. But if we had a trans version of the same molecule, now your dipoles are going in the opposite directions, and the resultant, because these electronegative elements are exactly the same, exactly same dipole values, you will have a zero overall resultant value. Any questions from how we figure out qualitatively? We are not doing any numbers. We are only doing zero and any. Zero and not zero. That's the only thing that we are looking at. We're not looking at any numbers. With our general information of what electronegativity is, what is the geometry and all that. Next part of our chapter. Oh, before I move on to the next part, any questions on polarity? Okay. So intermolecular forces. There are few intermolecular forces that you will need to remember. This is something that you've already done in your GChem, but I just want to remind you about few of these. And I'm writing these out in order of their strength. And I think that's the van der Waal or London dispersion. These are the 5 kinds of intermolecular forces that you have to know and remember. Out of all of these, the ionic kind, which has the electrostatic force between 2 ions, is the strongest one. Okay. Now, we will have to look at the ion dipole also, but let's go at one at a time. So ionic interactions are between ions. So if you remember your periodic table, one side is metals, the other is non-metals. Metals are positively charged, non-metals are negatively charged. So whenever you will have a metal ion and a non-metal ion interacting, when you have these formal charges, not only in this case, but let's say that you have a sodium ion also. So in organic chemistry, that's what we are going to see. This is inorganic. This is organic. Why? Because of the hydrocarbon present. So whenever this counter ion, metal counter ion will be present, you will have a formal charge, making this an ionic bond. And that's what you have to be able to be recognizing. When you have an ion dipole, let's say that you have an ion dipole. In your system, you have a molecule like this. This oxygen is ideally neutral. Why? Because this oxygen already has its 2 bonds and the 2 lone pairs. But in presence of a metal ion, there develops a dipole. So remember, this oxygen is sp3 hybridized. Its atomic geometry is tetrahedral, but its molecular geometry is bent. Right? So both these lone pairs are on the same side, and there is a resultant dipole that we see. So this resultant dipole interacts with this ion. Now you will usually not see these examples, but if you do, don't get flustered that we have never seen any setup like this. So your dipole can interact with a metal ion. And this usually happens with oxygen. Another example that I would like you to see is when you have a ketone. Where is the dipole here? Between the carbon and oxygen. If there is a presence of any metal ion, this metal ion and this dipole can interact. Okay, so this kind of interaction is also considered very strong, stronger than the hydrogen bonding itself. Now, hydrogen bonding indeed is a very, very strong kind of a bonding. But when does hydrogen bonding occur? Hydrogen bonding will occur whenever you will have a hydrogen next to an electronegative atom only. At that time, when the hydrogen is next to this very electronegative element, hydrogen will carry a large partial positive charge. So going back, when you have an ion dipole, you have a complete formal charge and you have a dipole. But in hydrogen bondings, you have what we know as partial charges. So your oxygen will be, or whichever your electronegative element will be carrying the large, because it is very electronegative, will be pulling out more electrons. It will be sucking more electrons out of hydrogen, leaving this hydrogen electron deficient or partially positive. So we generally like the delta sign like this. If anybody does not see what I just wrote. So this delta positive can attract other partial negative charges. So I'm going to write R here. R generally means alkyl groups. So let me see if I have another molecule, ROH. So this will be attracted to this, right, from another molecule. It may be the same molecule, it may be the other molecule also. So even though okay, hold on, I see a chat here. Is this PowerPoint on our Brightspace? Yes, this is from your module 1. This is on slide 40. Does that answer your question? Okay, good. So when these hydrogen bonds are forming, we usually denote them with dashed marks. Okay. So within the same molecule, if there is a hydrogen bonding present, what are the properties? How the properties will change? They will become very strongly attached to the other molecule, right? Because of this extra hydrogen bonding. Plus, their solubilities, their boiling points will also change. Okay, even though hydrogen bonds are very strong, they help develop extra bonding with the other molecule. They are still weaker than the covalent bonds. The covalent bonds are the sigma bonds that we are looking at. So this is the example. This is one of the examples that I found for your hydrogen bonding. Okay. The hydrogen in this case is known as the hydrogen donor, and this oxygen or the electronegative element from the other molecule is known as the hydrogen acceptor. Now, interestingly, when you do not have a hydrogen on your electronegative element, this oxygen can still behave as a hydrogen acceptor. Okay, it's not a very strong hydrogen bonding. So just imagine you have a ROH, and then I'm going to write R prime OH. So this oxygen is hydrogen bonding here. This hydrogen is hydrogen bonding here. But if you have a ketone right here and I have water molecules, this oxygen will also be able to do at least one hydrogen bond. Which will be a stronger bond? Of course, this, where you have two hydrogen bonds. This has only one hydrogen bonding happening. So this is definitely weaker than this, but there is some hydrogen bonding that is occurring here. So when you draw out your molecule, when you see any molecules, you have to remember what kind of interactions are happening. Any questions so far? So if you look at this example, the trimethylamine, ethylmethylamine and all, you will see how many hydrogen bondings can occur here? At least two. How many hydrogen bondings will occur here? Only one. And we can see the difference between the boiling point. More energy will be required to break these hydrogen bonds. Still, energy will be required to break this hydrogen bond, but not as much as is needed for propylamine. Similarly, if you look at trimethylamine, there is no hydrogen bonding will be occurring here. And so the boiling point, there will be practically no energy needed to boil this out. Okay, so if you compare all of these three, the higher the amounts of hydrogen bonding will be, the higher amount of energy will be needed to separate out the same molecule. And hence your boiling points will be very high. Now, a definition that all of you will be needing probably in 3 or 4 days is what is a protic material. Protic materials are compounds with hydrogen atoms which are able or capable of forming hydrogen bonds. Now, if you look at all of these, where is the protic hydrogen? This oxygen has a hydrogen, so definitely this is going to do hydrogen bonding. Is there a hydrogen on this electronegative element? No. So this is not a protic material. What about methylene chloride? This is the electronegative element, but is there a hydrogen on it? No. So this is also not a protic material. What about the DMSO or dimethyl sulfoxide? Oxygen is electronegative and sulfur is also electronegative to some extent. But is there a hydrogen on either of them? No. So this is also not a protic material. Any questions on what is protic? Protic materials will be able to do hydrogen bonding. For example, triethylmethylamine does not have a hydrogen on the nitrogen or the electronegative element, and hence it is not a hydrogen bonding material. The next important part is the lone pair dipole-dipole kind of a force. Now these forces result in neutral but polar molecules. So we just saw ketone. So when the dipoles line up, their opposite charges will act as if they are doing a dipole-dipole interaction. So having a dipole in the molecule is also important. If you have a neat material, what will be the partial charge on this oxygen? Negative. What will be the partial charge on this carbon? Partially positive. Similarly, another molecule of this acetone or this particular functional group, this carbon, which is directly attached to oxygen, will be electron deficient, whereas this oxygen will be electron rich. So this negative will line up with this positive charge. Overall, the molecule is still neutral. There is no difference between the charges. You just have to understand how these neutral and polar molecules are lining up. Any questions? Okay, understanding your these molecules will be very important for all of us. The last intermolecular forces that we will be looking at are the London dispersion forces. They are also known as van der Waal forces. But these are fleeting attractions between two molecules resulting from constant motion. So because there is a constant motion between two electrons in the same molecule with uneven distribution, we say a van der Waal force will exist. So if you look at this molecule, because of the friction between two molecules, one area will become partially negative. This will be the partially positive area. Again, because of that uneven distribution of electrons, one part is partially positive, partially negative, partially positive. Line up. This is your partially negative area. So these are balanced with positive charge of the nuclei, but this is a temporary dipole. This is not a real dipole. So this creates or induces this uneven electron distribution, induces a temporary dipole in the neighboring molecules. Now, one of the things that all of us have to remember is the more the surface area of the molecule, the more dipole will be possible. And that is why when we have bigger, larger molecules, and let's say I have these two molecules of the same compound. Okay, I just drew them in different colors so you can see that they are two different molecules, but of the same compound. When they are packed in a linear fashion, look at the surface area. It's so large. And so this will help. This friction or this movement against each other will cause uneven distribution of electrons. Okay? So the packing is so good because of this surface area. It will take a little bit more time to heat them off. So 1, 2, 3, 4, 5, 6, 7. But instead, if I have a branched structure, CH3, 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 CH3. Let's say I did branching of my 7 carbons and it gets a spherical shape. Who do you think will be easy to boil off? The circles who are unevenly packed, there's not good packing, or linear structures which are packed tightly? The linear structures, because it'll take more time to disturb the packing between them. Whereas it will not take much time for your packing to be disturbed in spherical shapes. And so this brings us to our next step, which is the, so this is just the repetition. This slide, which is in your module 1, slide number 46, will give you a brief realization of what intermolecular forces can do for you and how they are important, what kind and what example. So this is like a general reminder. So there are 2 properties that you need to know. The first property is boiling points. And I'm going to make a chart here. I wish all of you will also make this chart. I think it is in your sequence sheet also. But I just want to remind all of you what is commonality between a solubility and boiling point. So we are going to look at boiling points And we are going to look at solubility. Not just any solubility, solubility in polar materials. Example, water. So how does a structure affects boiling points? How does a structure affects the solubility? The first and the common thing is intermolecular forces. And you have to remember, ionic will have higher boiling points. Ionic will have high solubility in water. If a compound only has London forces and you have a compound who has ionic forces, who out of these two will have a higher boiling point? The one with ionic forces in it. Similarly, for solubility in water, if you compare a molecule which only has van der Waals, and if you compare a molecule with who has ionic forces also present, the one with ionic forces will always win. And I forgot to mention you, van der Waals or the London dispersion forces are present everywhere. If not everywhere, at least 99% of your chemical compounds have van der Waals forces. So for example, if I draw out this structure, what all intermolecular forces do I see here? Between this part, the non-polar part, I see the van der Waals forces. Between this part, I do see a dipole kind of a force. Why? Because between carbon and oxygen, I will have a dipole. And between these two, what do I see? I see hydrogen bonding. So overall, I say there is hydrogen bonding in this molecule. Compare it to a molecule which just have, instead of these three atoms, these three atoms. What all bonding forces do you see here? Only van der Waals. Who out of these two will have a higher boiling point? The one who has the higher intermolecular force. Who has more solubility in water? The one which has more intermolecular force. Okay? So this is a common term, molecular. Okay. Intermolecular forces. So more means more. Same here. More means more solubility. More or higher boiling point. Okay. The next is number of carbons. And this is the order that you must also compare your compounds. Whenever you're given any structures, you have to look in this order. As the number of carbons will increase, the surface area will increase. And that will more means higher boiling point. Unfortunately, that is not the case for solubility. More means low solubility in water. Why? More number of carbons would mean that your non-polar nature is increasing. This is a polar material. Non-polar and polar are not like materials. If you have a like material, then your like material will dissolve it. But unlike materials will not dissolve it. So a maximum of 4 to 5 carbons can be soluble in water. After that, they are insoluble in water. So as the number of carbons will increase, your solubility in water will decrease. What will happen to your solubility in a non-polar solvent like pentane or hexane? As the number of carbons will increase in your non-polar solvent, then your solubility will increase. But in water, it will be less. If your number of carbons are also same, what is the next thing that you must look at? Then you look at Branching. Branching just indicates if you have linear structure or any side chains on it. Branching decreases, lowers the boiling point. But what does branching do to your solubility? As your number of carbons increase and branching also increase, branching will decrease surface area and hence it will increase solubility in water. Why? Because the more spherical nature there will be, the more water can aggregate around that organic molecule. And the more aggregation it is, the more feeling of solubility that molecule will get. Any questions? So this is a very important chart. Let's try and look at a few examples here. Okay, I have this. So go ahead and you can also draw these out. CH, OH, CH3, CH2, O lithium, CH3, CH2, CH2, OH. And then I have CH3, CH2O, CH3. So let's label these. Go ahead and draw these out in your notebooks or paper, wherever you're writing right now. So looking at all these 4 structures, right? Which of these will have the highest boiling point and why? So let's do a poll here. Okay. So why don't you think about it while I will generate our poll. So anyone wants to say, have any question or state how we're going to start about it? Nobody? Okay. So let's look at the intermolecular forces again. Okay. So we are trying to figure out who has the highest boiling point. So the intermolecular force, where is it highest? What is the kind of forces that you see here? Yes, we do have a oxygen and a hydrogen. So there is hydrogen bonding here, right? What about this one? This one also has hydrogen bonding. So how are these two different? There is some branching also there. So if you compare these two, just these two, which have the same functional groups, OH, who will have a higher boiling point? The one, so let's look at branching decreases boiling point. And so this one will have a lower boiling point than this. Any questions? So there is C more than A. There might be other compounds in between, but let's just look at this for now. You have to compare similar molecules first. So go with the same polarity first. OH, OH. We are done with it. The next is this ether. Now, usually you must draw your ether like this zigzag motion. Because if you draw it in this way, you will say, oh, the overall dipole is 0. Is that true? No. Remember, there is some dipole on this ether. But is it enough? Is this dipole enough to compete with hydrogen bonding? No. And so D will have your lowest kind of molecule, right? It will have the lowest boiling point out of all of these. And so what happened to this guy? This has a formal charge on it. And so the kind of energy or molecular force that we see here is the ionic kind. And so out of all of these, this will have the highest boiling point. Weakest boiling point, highest boiling point. Okay, so you have to be careful about, go with the first polarities, okay? Go with the same polarities first. Check out the same polarity first. Then check molecular weight. What does that mean? 3 carbons, 3 carbons, 2 carbons, still 3 carbons. So their molecular weights for your class will generally be the same. But if your molecular weights are not same or are same, then you go with branching. Remember, branching has to be the last thing that you look in this order. Okay? So are you all ready for the poll? I will give you 1 minute to answer this. Out of all of these compounds, we looked at the boiling points, right? We did not look at the solubility. Solubility will be a little different. Now, the solubility rules that I have given you are for solubility in a polar material like water. So my question to you is, out of all of these 4 compounds, which will be most soluble in hexane? Okay, so what is hexane? Hex is 6 carbons, 1, 2, 3, 4, 5, 6. Throughout, hydrocarbon, no other priority. Did I say any other substituent? No. So what kind of a group is this? This is a non-polar material. So I'm not asking in a polar material. I'm asking you in the non-polar material. So you will see the poll now in front of you. Okay. I see most of you doing it right. Okay, very good. Okay, very good, very good. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Wait, I have a question.
Okay, go ahead.
Okay, so you see how for B you says ionic bond? Why isn't it the same for C?
So there is no complete or formal charge on your C. You see that? There is a hydrogen bonding available, but not a formal charge available here.
Okay, thank you.
Okay. Okay. So with this part, the answer will be D. The reason is all of these are very strongly soluble with water. The least soluble in water will be this part. This molecule with just dipole-dipole interaction. And if you remember our intermolecular forces, dipoles are way below here. Ionic will be giving you the strongest solubilities. Hydrogen bonding will be giving you also be giving you stronger solubilities. But the dipole-dipole interaction will give you the least solubility in polar materials. And hence, they will give you high solubility in non-polar material. Any questions? Okay, you know what, let's do one more quickly, just for all of our understanding. Let's see, I have So I'm going to label them as A, B, C, and D. So I'll keep my rules next to me because I'm still new at this. Okay, that's what you should do. Let's see if I can fix it. So what is the first thing that I should look out for? I should look out for same polarities. So this is the only different one. This is the rest of these are alkanes, complete alkanes. This is my only alcohol that I see here. So among all of these three, this one has hydrogen bonding also. None of these have any hydrogen bonding. So I know that if I have to judge my boiling points, A will have the highest boiling point. If I have to compare my solubility in water, A will still be the strongest soluble or highest soluble in all of these materials. Let's look at the others. Now their molecular weights are a little different. If I count how many carbons do I have here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So among all of these three, D has the highest van der Waal effect. And so in boiling points, in terms for boiling points, my D will have the highest boiling point. Remember, the more number of carbons, the higher the boiling point will be. So D is going to have my highest boiling point. Among these two, branching lowers boiling point. So if I have to compare these two now, my C will have a lower boiling point because they are same number of carbons. Branching lowers boiling point. So if I compare these two, B will be higher in boiling points and C will be lowest in boiling points. Now, using this, I can use the solubility in water also. What does solubility in water tell me with carbons, number of carbons? As the number of carbons increase, the solubility in water decreases. So among all of these, we know that A is going to be the most soluble with its hydrogen bonding because I'm following the same rules. But what will happen with number of carbons? My number of carbons are most in this molecule. And so instead of being a high boiling point material or high solubility in water material, this will be my lowest in solubility of water. More surface area means low solubility in water. Then I compare these two, which are less in number. And so I see that branching increases solubility. So decrease in surface area or increase in branching increases the solubility in water. So out of B and C, C will have more solubility in water, followed by B. Same molecules, same molecular forces, how it affects is different. What will be the solubility in hexane or pentane or decane or octane or any non-polar material will be? Whatever solubility of water you have chosen, exactly opposite. So if D is lowest solubility in water, it will be highest solubility for hexane. And if A, which has hydrogen bonding, has the highest solubility in water, will have the lowest solubility in hexane. So exactly reverse order. Oops. This is something that we all will have to practice more also. Any questions?
Can you explain why C for the solubility in water in the
Uh-huh.
option?
So you see how branched it is? So it gets a spherical structure to it. So there are 1, 2, 3, 4, 5 carbons and 5 carbons here also. 1, 2, 3, 4, 5. So the surface area of these 5 linear carbons is more surface area. And with more surface area, your van der Waals forces, they increase. And van der Waals forces are popular for non-polar materials, but not for polar materials like water. So you wanted to know about the boiling point or the solubility?
Solubility.
Yes. So as your molecule gets lower solubility or more spherical nature, the water molecules can aggregate better around it. It can surround it better. But if it is like a long molecule, it's long spherical area, more water molecules will be needed, to surround or aggregate it. You see? So in the same amount of water, spherical or branched compounds will dissolve more, whereas in that same amount of water, longer surface area or larger surface area molecules or linear chains will dissolve not very well. Does that answer your question?
Yes, thank you.
Okay. And so with this knowledge, we are going to learn more about alkanes. Now, if you remember alkanes, in which we have covered a little bit in the nomenclature part also, they are saturated hydrocarbons with no polarity at all. Or there is a carbon-hydrogen bond, but there is no electronegativity difference. So we don't say they are polar. We say they are non-polar bonds, non-polar materials. And as we saw, they are relatively unreactive because of this absence of polarity. They are quite stable and not soluble in water. So carbon 1 through carbon 5, only these structures. So 5 carbon containing compounds are only the ones which may be soluble in water. Okay. So these are important for us, the alkanes, because all our fuels and plastics, they are made up of alkanes. Now in this particular module, module 5, we will look at another kind of isomers, which are known as conformational isomers. Now if you remember, the first kind of isomers that we looked at were constitutional isomers. Then we looked at geometrical or cis-trans kind of isomers. Both have same molecular formulas. So if you have two constitutional isomers, they will have same molecular formula. If you have two geometrical isomers, you will have same molecular formula. That's the main consideration for any isomer. The only difference is different connections. But in this part, you have same connections. So your stereochemistry is same, but there is different orientation around the double bond. That is the only difference that we see between these two. Now, usually IUPAC nomenclature can also help you. If you have the same IUPAC name, for example, if I have this molecule and I have this molecule, if I use the IUPAC nomenclature correctly, I can still figure out if they are the same molecules or different molecules. So let's look at these 3 examples. And I've just rotated a few bonds here and there. What would be the name of this compound? But-2-ene. Why but? 1, 2, 3, 4. 4 carbons. Alkene is at the second carbon. 1, 2, 3, 4. Similarly here, but-2-ene, but-2-ene. To a normal layman, all of these are the same compounds. However, to a chemist like you who's learning organic chemistry, you must know this is incomplete nomenclature. We have to take into account what or where is the priority group. On this carbon, you have a hydrogen and this priority group. On this carbon, this is your hydrogen and the priority group. Both priority groups are exactly the same. They are on the same side. So we label it as a cis-2-butene. On this carbon, hydrogen is here, priority group right here. On this carbon, hydrogen is here, priority group is right here. Both priority groups are on the opposite side. Not cis, this is trans. So helping with IUPAC name will also help you. So is this molecule and this molecule exactly same? Yes, they are, because I just rotated it or flipped it, or you are viewing it in a different view. So how we view a molecule in 3-dimensional space will also create more isomers. So in this case also, your both priority groups are on the same side. So we say they are exactly same. These two are same, even though they look different, but this is definitely different from these two. So when we look at our alkanes, and we looked at the boiling points and solubilities, we will look at conformational isomers now. These are the third kind of isomers that you will need to know about. No. What happened? So in here, I have these two tetrahedral structures. Okay, remember I was telling you there are two V's coming up, two V's going down. And I have these two carbons. Conformational isomers will only exist when you have more than two carbons. So this is a tetrahedral carbon on its own, and all of these white circles are its hydrogen bonds. If I remove one of these hydrogens and I insert or make a bond with another carbon, remember the tetrahedral structure, I will have two carbons oriented like this. There are different ways by which I can look at these two carbons across this single bond. When two carbons are connected to each other, we will see that across this single bond, the rotation can occur freely. Now, unlike double bonds, let me see. So this is my double bond. These are my two carbons. They are in planar view. And you see the double bond here. There cannot be any rotation across this double bond, and I'm trying to break it. I'm not trying to really break it, but if I try to rotate it, it's not rotating. So conformational isomers will only occur between two carbons and on their single bond. Okay? So the groups joined by these single bonds undergo a change in their relative positions when the bonds are rotated. So let me show it to you so you can see better. I'm rotating my top carbon. All the groups are now rotating relatively. But I had to hold on to one of my carbons. So I was holding on to my bottom carbon while rotating my top carbon. So conformational isomers have same molecular formula. Conformational isomers. So they have same molecular formula, same connectivity, but different 3D shapes. Why? Because of rotation along the single bond. And which single bond are we talking about? Between the two carbons. So for our course, we are going to have only two carbons. And conformational isomers, they differ in 3D orientation and hence often have different energies associated with them. So if you look back at constitutional isomers, 1, 2, 3, 4, OH. If I have a molecule like this and I have a molecule like this, both of them are constitutional isomers, right? I can see the difference in connectivity. They have different properties. Similarly, if you have these geometrical isomers, You can see the difference in energy here also. While both of these groups are bumping into each other, these groups are away from each other and hence not bumping into each other or causing any energy difference. So the groups away from each other are causing this molecule to be more stable and hence lower in energy. So conformational isomers are even though same molecule, it is just held in a different rotation. Oops, share my screen. So again, you can read a little bit more on this slide, but let's more examples. So we have started looking at our structure in a different way, in a 3D way, and that's what all of you are expected to do. When I think of carbon now, I always think about its tetrahedral structure. Okay, so this is the tetrahedral way I have to think, or you have to think about your molecule. Two of the bonds will always be in plane, while two of the other bonds, one of them will be coming out to you and the other will be going back from the plane. And so this is the wedge and the dash bond. So this red line right here is coming out of the plane. Which plane? This plane. So let's say I have my hand as my plane. Can you see the back bond? So I will keep these two bonds in the plane. One of the bonds is coming out towards you, which is going to be the wedge. And the other one, which you cannot see, is going behind the plane, is going to be the dashed bond. So if you think about the wedge and the dashed bond, remember to draw the tetrahedral. Most of your questions will be dependent on two carbons. Okay, so how about all of you draw this with me? So what did I draw here? Oh, here we go. So I have these two carbons. Each of the carbons have their own three bonds, three groups on it. So what I have drawn here is two of these bonds are in plane. Let me say that these two are in plane. Then this bond right here is coming out and this wedge is going at the back. Similarly, on this carbon, this bond is coming out and this wedge is going at the back. Now, I have shown the wedges and the dashes like this. You can draw your dashes and wedges like this also. Oops, I'm making exactly same. So, you get in a habit of same drawing. That's what I draw. So let's go ahead and draw with me. I'm going to keep my molecule right here so all of us can see. I'm first going to draw this linear part between the two carbons. And then I have chosen these two to be in my plane. Okay, these are in my plane. Both of these are pointing upwards. So both my planar bonds are pointing upwards. And as you can see, it's not straight, it's at a little slant. So that's what I'm going to draw here, my little slant here. Now one of the bonds is coming out. One of the bonds is coming out. This bond is also coming out. On the other hand, this bond is going at the back. So that's my dash. And this bond is going at the back as well. So that's my dash, another dash. Now, why did I draw this? I'm going to label them as X, Y. Both my groups at the back, I'm going to label them as X. Both my groups in the front, I'm going to label them as Y. Don't worry about that. Is everybody with me? Is there anyone who has not drawn this yet? So now I'm going to do a rotation. I'm going to keep one of these carbons and I'll label this as carbon 1 and this as carbon 2. I will keep one of these carbons where they were and I will only move this carbon. Remember I showed you that I have to hold on to one carbon and only move the other one. Okay? So if I'm going to do this, I will have to repeat my single bond right here. This group going up, this group going out, this group going at the back, X, Y. But what will happen to this? If I will make a rotation and somehow this planar bond is not in the same vicinity, not in the syn vicinity, now it is in the anti vicinity, anti to my this group, anti to my this group. So I have this molecule and I am rotating it so that now this group and this group, where my thumbs are now, they are in the opposite orientation. This bond is still there, this bond is still there, this bond is still there. All of these are still my planar bonds, okay, same plane bonds. But what has happened to my Y and X? When I rotated this, and let me take one of these out so you can see it also. Let's say this was my Y. I have this molecule which is moving and my Y is also moving, my X is also moving. Instead of being in their original places, my Y is now at the back. And my X, which was earlier at the back, is now in the front. So let me show this to you again. This is my original planar methyl group or whatever group that is. This group which is coming out of the plane is my Y. This group which is going at the back of the plane is X. And I'm rotating my planar bond from one view to the other. And I see that my X is now coming out, my Y is going at the back. So this one rotation is not even complete rotation. Okay, I just did a little bit of rotation. But I see that the relative positions of my groups have changed. So this is my wedge and dash view. Let me just go back and do another view like this. So I'm not looking at right in front, back to back. I'm not doing that. I'm doing a side view. This is complete side view. This is partial side view, which I'm going to show you. So I'm going to do a partial side view like this. For the same compound, I'm going to do a side view, partial side view, sorry. So this is my carbon 1. I'm going to start looking. So this is my I. I will keep my carbon 1 right here. So if I'm looking from this angle, where is my Y and where is my X? To my I, my Y is on my right. To my I, my X will be on my left. So I'm going to draw this as a dot. This group is going up. One of the groups is going like this. One of the groups will go like this. This is my carbon 1. This group right here, my Y to my right as I'm looking at it, my X to my left. Exactly like this, I will draw my C2, a dot. This group is going up, X right here, Y right here. But I drew this one a little smaller. Why? So I can connect these two bonds. And so this is a sawhorse projection. This is a wedge and dash kind of a projection. This is my sawhorse projection. For this also, I'm going to draw these compounds. For this carbon, I'm going to draw this way. Remember, this is going down, this is going sideways. My X and Y are on the same direction. X and Y are on the same direction. Let me put it X prime. Y prime, X prime. Y prime, sorry, not this one. Y prime, X prime, X prime, Y prime. Who does not understand this part? So remember, I made C1 and C2 a little different. How? I made C1 here and I put C2 a little above it. We call it a horse kind of projection because it seems that a person is going to ride this horse somewhere. But this is like a partial side view. Now let's try a Newman. A Newman is going to be our back-to-back or completely obstructed view from the top of the molecule. So same molecule, I'm going to draw again. C1, exactly same features. I have my C1. There is a group going up. X right here, Y right here. Okay? And at the back, I will draw my C2 as a big circle. So the back carbon is my C2 carbon. Both of these are going upwards. Y prime and Y are in the same direction. And so this is my Newman projection. So instead of drawing like a perfect circle like this is what your structure would look like. If you have a wedge and dash, you can draw your Newman. If you have a sawhorse, you can draw your Newman. If you have a Newman, you can draw these two as well. So let's try this one. C1, C2. So C1 is right here, X, Y. I have this circle. This group is going down. X prime is right here. Y prime is right there. So this is my complete front view. This is my complete side view. This is known as wedge dash structure. This is known as sawhorse projection, and this is known as the Newman projection. Okay. Let's do another example, and all of you should be able to do this with me. Let's say I give you a structure like this. How are you going to do the Newman for this one? So I just want to remind you, before you start doing anything, think about your nomenclature. Where is your number one carbon going to be? Will you be starting from your left, or will you be starting at your right? Kara Weston, are you here?
Yes.
Okay, so which direction are you going to start your numbering of carbons from? From your left or from your right?
Would it be your right?
Very good. And do you know how many carbons are there in this molecule?
2.
So 1, 2, 3, 4. Okay, thank you, Kira. This was a trick question actually. Just remember, because it appears in the side chain, that does not mean that you will forget to look at your longest chain. Always look at your longest chain. Oops. Okay, I hope all of you are drawing this out with me. Now on this particular structure, because there is a dashed group at the back, how many bonds do I see here? I see the 3 bonds, and my hydrogen will be the 4th bond, which is hidden usually. So my methyl is going at the back. Where will my hydrogen go? It will go in the front. What about this carbon? On this carbon also, I will make a dash and a wedge. So remember, your hybridization will tell you the geometry. Your geometry tells us that we always draw these as zigzags, and the zigzags, inverted V's, are what will help you look at your other groups. Okay. So in this particular question, I'm not going to draw across C1 and C2. I want a projection, a Newman projection across C2 and C3. Now, depending on what your question is, your question may ask you to draw the C2 in the front or C3 in the front. So if that is asked, look from that direction. Let's say I ask you to draw from your C3. So you will start to look at this. What is this? This is your carbon 3. And I'm going to draw it. What is on your right hand side? A hydrogen. Where is this hydrogen? It is pointing up, pointing up, pointing up on your right. Where is this hydrogen? This hydrogen is also pointing up on your left hand side. So pointing up on your left hand side. What about this methyl group? On the same carbon, you have this methyl group also. And I can leave it like this. Now I will draw my C2, which is at the back. What is on my C2? If you look at the C2 from the same eyes, you have to look at the same location. What is going up in the planar bond? Up in the planar bond is the chlorine. Very good. What is going in the right? Down. Right? Down is the hydrogen. And what is going in my left? Down. This is going left, down is your methyl group. I did not do anything else, but I have my Newman projection in the perfect order. Now, this is the time that you must understand a dihedral angle also. When you have a dihedral angle, it is always between 4 atoms. And 2 of those atoms are the carbons across the double bond. So how do I look at any dihedral angle? There is this hydrogen, there is this carbon, and the carbon at the back. So you see my 2 atoms. Of the 4 atoms, 2 of my dihedral atoms will always be the carbons of my single bond rotation. So 2 of those, hydrogen and this chlorine. So this is a dihedral angle. What is the dihedral angle between the chlorine and hydrogen in this Newman projection? It is a 60 degree. How do I know that? Across a circle, there are 360 degrees maximum possible. How many divisions do I have? 1, 2, 3, 4, 5, 6. If I divide it by that equally, I will get a 60 degrees. So this version where your dihedral angle has 60 degrees, or when your dihedral angle between these four atoms is 0 degrees. These conformations and the conformations in between. So dihedral angle is 0, 2, 3, 4, 10, 20, 30, 40, 50, 60. Then 65, 85, 95, 120, and so on and so forth. So your dihedral angle and your ability to recognize what is the dihedral angle between this chlorine and this methyl. 60 plus 60 plus 60, 180 degrees is the dihedral angle between this chlorine and this methyl group. So remember, between the dihedral angle, two of the atoms are the carbon atoms involved in the molecule. Any questions so far? So very quickly, let's look at ethane. Ethane, which is the most basic two-carbon molecule, is where the conformational isomers start to appear. So if you look at the first isomer, conformational isomer, which looks something like this, we see that the interconversion of one conformation to the other is a dynamic process. The only problem is we cannot isolate these isomers from each other or separate out these conformational isomers. So if we start at the first position where hydrogens are back to back, and I want you to pay attention to these starred hydrogens, these back to back hydrogens are eclipsing each other, which is not very favorable. And so the potential energy is very high. Okay. Now, as you move your angle, so we are starting to move one of these hydrogens, and remember the dihedral angle. Now the dihedral angle between these two starred hydrogens is 60. And we say that the conformation is staggered. Observe that there is a low energy. This is not zero energy. The molecule is still moving. Okay, the molecule is still moving. However, the potential energy at this point with staggered conformation is 0. There is literally no energy associated with it. What does that mean? It means that staggered is a very stable conformation. Okay, so as the angle changes, and it is now 120. So between the hydrogen in the front and the hydrogen at the back, the dihedral angle is now 120. And so again, it is eclipsed. All of the hydrogens are back to back or eclipsing each other. And now they have again become high energy or less stable. So the eclipsed and the staggered, the energy difference is between these two only. There are only two kinds of conformations available for ethane. And if you look, the energy difference between all of these is between 0 and approximately 12. Now, I will explain to you why is this so, but let's very quickly look at ethane. I'm sorry, butane. In butane, unlike ethane, where all your energy differences were between 0 and 12, in butane, we have energy differences right here and then right here also, right? And so the energy differences in butane are because of these bulky methyl groups. and the location of these methyl groups relative to each other. So today we are going to learn about two new strains. One of them is known as a torsional strain and the other is the steric strain. So torsional strain is present only in eclipsed conformations. What is eclipsed conformations? When you have back to back, right? So this is what your eclipsed conformation will look like. Why? Because the electron repulsions between the bonds is maximum here. The second strain that we looked at today is known as the steric strain or the space strain or the non-polar strain, and this is present only when bulky groups or any other group other than hydrogens are very close to each other. So just imagine two carbons, and I'm not going to draw all of the wedges in the dash. Just imagine the same plane, the same planar bonds. You just have hydrogens. On the same two carbons, on one of the carbons you have hydrogen, but on the other you have a methyl. What does a methyl look like? Something like this. Do you see how this bulk has changed? And now, remember the slant? Remember the four polar bonds? Both these methyl groups bumping into each other. And that is why we get the steric strain also in butane. Torsional strain will only be present in eclipsed conformations. Steric strain will be present when there are bulky groups other than hydrogens. So that will be present in your staggered conformations also. So this is staggered conformation, and this will be your, oops, don't worry about the others. This will have torsional plus steric. This will only have steric strain, no torsional strain in this molecule. Okay, any questions?